Good morning, everybody. My name is Dr. Pete, and I'm here for a Friday morning 7 a.m. show. I either do my shows live on Fridays at 7 a.m. or I will release a production style video. And in today's broadcast, we are going to talk about why we are sick. And specifically, this is a topic when I say why we are sick, sick with what? And in this presentation today, we're focused on chronic disease. Now, again, my name is Dr. Pete. I'm a PhD biochemist. These days, my my efforts lie in understanding metabolic pathology. So, trying to understand what is driving chronic diseases like gout, diabetes, obesity, cardiovascular disease, and so on. I'm also a nutrition network coach practitioner, and my programs are recently accredited by uh, the Society of Metabolic Health Practitioners. So most of you know me based on the presentations that I give on gout. And what I always point out at the beginning of those presentations is that gout is a systemic issue and most likely is being driven by fructose uric acid metabolism. And what I tell people outside of the gout circle is that the reality is that I'm an expert in the area of fructose uric acid metabolism and how it relates to other important metabolic pathways that humans utilize to process energy. And that's really what the topic has to do today. What is driving these diseases? And I think it's very, very important that we approach this issue from mechanism. And sometimes I get criticized about that because it's like, well, Dr. Pete, why do we need to know this? Why do we need to be in the weeds about this? And the main reason is because if you really want to understand how to approach reversing those diseases or not ending up expressing those diseases in your lifetime, then we need to understand more specifically how they're being caused. Because if we can understand how they're being caused, right, if we can get to that issue, and I'm not claiming that I know the answer to that, right, but mechanism is the way to get there. Understanding the chemical relationships that are happening in a cell and how we get to these inflammatory states, and the pathological way that we manage calories that are coming in. If we can understand that, then we can come up with strategies in how we eat. And then there are other lifestyle issues here: exercise, sleep, stress reduction, all that business. Yes, I understand that. But at the pinnacle of this, what our eating lifestyle looks like every day is super important. So let's go ahead and get started with today's presentation. Why are we sick? And the elephant in the room, and you can see the lists of all these diseases. They all, at the core, are metabolic in how these diseases are generated. And we're going to talk in a broad way about this today. We're going to look at the statistics and even the costs of these diseases on our society and so on. But then we're going to get into the weeds with this. And then we're going to end in a place where I'm going to suggest an eating lifestyle that works best for at least one of the eating lifestyles that works best for reversing these conditions. So remember, we're going to go through some statistics right now. However, all of the diseases that I have listed here are metabolic in origin, and most of them, I believe, are being driven by the hyperactivation of the key metabolic pathways that handle glucose and handle fructose, and heavily influenced by the amount of these macronutrients that are arriving. And today we're going to focus on the liver, but there are other organs too. Hopefully I won't forget to mention them, that are processing these macronutrients in a hyperactive way because of the amount of these macronutrients that are arriving at the liver in a relatively short period of time. That's the thing. So these pathways are being overwhelmed. So when we look at coronary artery disease, which there's about 20 million Americans that suffer from this, this is the number one killer. About 7% of our population, yeah, it's a metabolic disease. It's being driven by the processes that I just was speaking about. Type 2 diabetes, 37 million people. And then we have to combine, though, the pre-diabetic aspect of this, of which there are about 96 million people. So that's about 40% of our population in terms of pre-diabetes. And the listener should understand that in 2016, I was diagnosed with gout. And then in 2019, I was diagnosed with pre-diabetes. And I've reversed and put those conditions in remission, the gout in remission, the pre-diabetes in terms of reversal. So I have gone through the process that I am talking about today, and I've gone through the stressors to sort it out, right? And it is the inspiration that led me to be sitting here with you this morning, quite honestly. Now, moving on, we look at obesity. We have 109 million people. This value, though, does not include when we combine the people in the United States that are also overweight. And when you combine those values together, we have a situation where over half of our country is suffering from obesity or significant overweight conditions. Hyperuricemia, this is the situation where people have high uric acid, chronically high uric acid, of which I'm one of those individuals. And this is one of the conditions. There are others, but this is one of the conditions that lead to a high probability that that individual will suffer from gout. Keep in mind that all of the conditions that we're talking about here are more prevalent the older you get. So I'm 64 years old. When I was diagnosed with gout, I was 57. And then the prediabetes hit me when I was 60. Alzheimer's disease. This is a metabolic disease. When you look at the depth of the literature and you see what's happening here, we have basically the marriage of two aspects. We have the scientists that are looking at this from the outside in, so they're looking at the plaques and the things that they can see essentially on the outside. And then you have the metabolic scientists that are looking at the fact that the brain metabolizes fructose, and we have fructose uric acid metabolism going on there. And we're going to be talking more in detail about this pathway today that can lead to the derangement that leads to Alzheimer's disease. And even though that population value, 6.5 million people, you can say, well, it's not all that much. But when you start to, this is total adults. When you start to look at the fraction of Alzheimer's in older people, you see that this percentage, the percentage of older adults with Alzheimer's or dementia, is starting to skyrocket. And the numbers are substantially going up as our population ages. High blood pressure, 121 million people. And these things are related. The hyperuricemia, for example, and hypertension, high blood pressure, those things are related. And then we have non-alcoholic fatty liver disease. That's about 62 million people in our population, 20 to 24%. And chronic kidney disease, 37 million. And again, as you get older, we see these proportions increasing. You see them disproportionately increasing with age. And that's because metabolic derangement that leads to these diseases takes decades for these conditions to appear. And usually when somebody's suffering from one, they also are overlapping with others. Now, the purpose of this slide is just to indicate the concept that I'm talking about here, which is the fact that you have overlap. So somebody that has high uric acid, and high uric acid is defined in men at values of 7 mg per deciliter of uric acid or higher, and in women it's 6 mg per deciliter of uric acid or higher. The normal range, if you go into a doctor's office and you have them measure uric acid values, the normal range is taken to be between 4 and 8 milligrams per deciliter, depending on the lab or the laboratory that's actually going to evaluate their work. In any case, if you are hyperuricemic, high uric acid, about half of those individuals also have high blood pressure. 60% of them, chronic kidney disease at some level. Over half are obese, a significant portion type 2 diabetic, along with kidney stones, and then a significant portion high risk or heart attack and stroke. So the point is, metabolic derangement leads to global issues at the level of our organs. This is not like a single point thing, like having a sliver in your finger, which can be fixed by taking a drug. If you listen to Dr. Robert Lustig, he's talked about this a lot. And in his book, Metabolical, he talks about the fact that these diseases are not druggable. And the reason they're not druggable is because they are systemic and they go too deep. Some would argue at the level of the mitochondria is where all this, the dysfunction with the mitochondria is where all this starts, which that question mark is the very reason why I believe that the answer to these things down the road is understanding mechanistically what's going on exactly. The costs to our society are staggering. Coronary artery disease alone, 216 billion projected annually. Diabetes, 324 billion. The obesity issue, around 173 billion. Alzheimer's is tapping in at 305 billion. I mean, think about how often we hear about a new Alzheimer's drug that's on the market that down the road is shown not to have any real effect on helping that situation, or a very small effect on it. Arthritis, I put that in here because if you look at the osteoarthritis data, which I have hundreds of papers, it's well known that hyperglycemia, high glucose taken in a chronic way in the lifestyle contributes to driving arthritis. In particular, how is that happening isn't really well understood, but the association is very, very strong. There's hundreds of papers where this has been looked at. And then we have to put cancer into this because many cancers are metabolic. Yes, metabolic. And that means that if you change the way that you eat based on good, solid, informed decisions, that you probably can influence preventative actions. And then if you are suffering from cancer, being able to improve the treatment by eliminating hyperglycemia, sugar intake, and so on. And then we have chronic kidney disease coming in at 87 billion. The main point here is that if you add these numbers up, we're over $1 trillion. Yeah, over $1 trillion. You know, and we have discussions all the time about the fact that Americans don't like their healthcare system and how expensive it is, and the issues with the insurance companies and all that. So just think about this, right? If we can understand better the metabolic drivers so that we can make intelligent decisions about how we eat, and then obviously other factors in there, but the eating thing is the big one, right? It's at least 85% of this deal, right? So if we can figure out better strategies for eating, then we can go to a much greater length of preventing ending up being one of the statistics here, right? Being part of this potentially of the diabetes expense. This is just a map that shows you the overlay of diabetes right now in our country. And the shocking thing is you can see it's prevalent everywhere. Nobody is escaping this situation. There are density demographics that have to do with where you live in the country. Everywhere where we have denser populations, you see that there are greater clusters of diabetes there. So, I mean, the main take home here is that this is really a big deal in our country. And then if you take and you overlay a map of obesity on the same map that we have here, you see that the clusters are essentially the same. And then if you ask the question, what proportion of the demographics here, what would this map look like if we overlay non-alcoholic fatty liver disease? And you see it tracks exactly the same way as the obesity and the diabetes, which is really a scary thing. And in today's presentation, very quickly here, we're going to start to get into the weeds. And I'm not going to apologize for that, because I believe with all of my training and everything that I understand about cellular biology, that understanding mechanism is how we get to a better understanding how to prevent these issues, right? And one of the questions that we see all the time, especially at the superficial level of the internet and with our medical establishment, is the chicken and the egg issue, right? Is obesity driving these derangements, or actually is obesity an endpoint consequence? And I'm arguing that the diseases that we started out talking about, the diabetes, obesity, cardiovascular disease, gout, these are all consequences of these central derangements in our metabolism. And a particular individual has a certain genetics associated with them, and how they respond to their environment will be skewed based on their genetics, right? How they respond to the improvement in their condition by exercise, how they respond to a certain eating environment, is what leads down the road to these consequences, of which we have this cluster. So this diagram is to give you some idea. I want to just talk briefly here about the non-alcoholic fatty liver disease issue. And on the left side of this slide, this is an individual where the imaging shows their liver. It's labeled here, and then underneath that, you can see literally how fat has basically intercalated all around the organs there. And this is an individual that is suffering from non-alcoholic fatty liver disease. And if this is a male, which I think it is, most likely, if you were to take a tape measure and measure their circumference over the top of their belly button, they're going to come out at around 41 inches. Their waist to height ratio is going to be 0.5 or greater. And if we were to look into their biomarkers, right, in a very meaningful way and in a very deep way, you're going to find a metabolic derangement in this individual. And then on the right, you can see a CT scan where they have cut straight across the human torso, and the normal, and they're comparing a normal liver to a fatty liver. And you can definitely see on the right the swelling and the density difference that has to do with the fact that liver is full of stored fat. And if the liver is in this condition, what you need to understand is it can't function right. It's not going to function right. And this is why you find non-alcoholic fatty liver disease in people that are diabetic, significantly obese, and even people that are suffering from cardiovascular disease as an example. Now, the purpose of this schematic is to give you an idea that because we're going to be focused today on what we're eating, right? So this is what you're putting in your mouth at any given time. And this diagram is important to understand how this is going to work. So you put something in your mouth and you eat it. Basically, when it reaches the intestines, those macronutrients are going to be delivered into the circulatory system. So we're going to have glucose delivered there. We're going to have fructose delivered there, amino acids. There's going to be fats. There's going to be a lot of things that cross that barrier, partially broken down, that enter into the blood supply. And in today's discussion, we're mainly going to be focused on the fructose and the glucose, and where those macronutrients enter into the port. It's actually going to be into the portal vein on its way to the liver, on their way to the liver, and as they make their way to the liver, they are going to pass by the pancreas, and the pancreas is going to respond to the glucose by producing insulin. So at the point where the glucose and the insulin arrive at the liver, now up to about half of that glucose is going to be processed out of the blood supply, and somewhere between 60 to 80% of the insulin is going to be cleared, so that on the other side of the liver, as the blood supply reaches what researchers call the peripheral circulation, which is going to be going to the skeletal muscle, adipose, brain, yada, yada down the road, that physiological, in an ideal setting, physiological concentrations of glucose and the amount of insulin needed to process that glucose into these other organs will be properly added into the circulatory system after this first pass through the liver. Now, there's a couple things that I want to mention here. As the glucose and the fructose enters into the blood supply as it exits the intestinal system, we also have the incretins or incretins that are released, the glucagon-like peptide 1, and also the GIP protein. And these are involved in firstly in enhancing the amount of insulin release by the pancreas in response to glucose. Now, what we hear in the literature all the time about the fructose is that it has no effect on fasting glucose. But here's the thing: there's current literature that has convincing evidence that the arrival of fructose at the pancreas hyperactivates the pancreas in terms of its insulin response to the glucose, right? That is a significant thing, because what it suggests is that more insulin is going to be released at the level of the pancreas than should be, right? And we're going to keep coming back to the fructose over and over again, because the central part of this, getting into the weeds, has to do with fructose uric acid metabolism. The other fructose effect that we have is on the receptor, the GLP-1 receptor at the level of the brain. And the interaction there with the fructose causes disruption of GLP-1 activity, GLP-1. And one of the fundamental functions of GLP-1 is to enhance satiety, right? So that your brain goes, okay, there's enough incoming glucose now, you don't need to eat more. And we're going to be talking about the fact that fructose, in a lot of different ways, causes somebody, when they're eating it, to increase the amount of calories that they're eating in that setting, to also generate compulsive behaviors and so on. I'm going to get more into this later. But one of the missing pieces of this, when you look into food addiction, or when you look into sugar addiction, for example, from a biochemical point of view, has been how can fructose modulate the effect of GLP-1, right? Because GLP-1 goes to the brain, and there are satiety effects, and the satiety effects are getting you to stop eating at an appropriate time as these calories are coming in. And fructose is having a negative effect on the GLP-1 receptor, which disrupts that satiety signaling. So an individual is going to eat, they're going to continue to eat when they should actually be receding from that aspect of it. So this slide is showing you a global perspective of what should happen when somebody's eating under physiological conditions. Meaning conditions that are not hyperglycemic, right? We're not overloading the system with glucose, and we're not introducing a high load of incoming fructose. We're going to talk more about that in a minute. And yes, alcohol is also going to have a contributing factor, but that has to wait. until the next section that we get into here. So I have had a lot of people either write into me or to question directly in the chat, which you can do this morning if you want, but I'll get to those questions at the end of the presentation. And they're asking me for more simplified explanations for the metabolism. So now what we're going to do is I'm going to try to gently enter into the weeds about this. And what you're looking at is a heavily idealized relationship between the two central pathways that lead to what I'm going to call pathology, right? The driver behind these chronic diseases that I've already listed out at the beginning of the presentation. On the left side of the slide, you're looking at glycolysis. This is given a light gray color. And when you read the literature, you get deep into the science, this is the primary pathway that handles incoming glucose, right? And any sugary thing, any complex carbohydrate that you eat in the diet, essentially is going to be broken down into glucose, fructose, and galactose. The galactose is, I'm leaving out of the conversation for today. The two primary issues here are how our cells handle the glucose that's coming in and the fructose, and the model system that we're going to focus on for the entirety today is going to be on the liver, since the liver is really the captain behind regulating what's going to happen essentially with those two macronutrients. And I'm not saying that other aspects in the peripheral circulation, like the adipose tissue, the skeletal, the chondrocyte, which is the primary biological cell in a joint, that is the concern of gout sufferers and so on. But we have to focus on an organ here to understand what is going on essentially overall, right? And the liver is the obvious choice because it's really the captain here. So the glycolysis, the glucose handling is shown on the left here in the light gray. And as glucose arrives at the liver and comes into the liver, remember what I said on that first pass, up to 50% of the glucose is going to be processed here. All right. And as the glucose comes in under physiological conditions, then the primary function of the glycolytic pathway is going to be to generate ATP and to fill glycogen stores. And I'm showing that here in this. So the glucose comes in, it's going to move through a bunch of steps that are highly regulated. The outcome designed to produce ATP for the cell. At the end of the glycolytic pathway, we have the formation of pyruvate and lactate, which both will be introduced into the mitochondria by another set of steps. And in the mitochondria, that factory, the energy producing factory, is going to generate large amounts of ATP. ATP is the energy currency that the cell produces that we use every day. Now, there are other small molecules that operate like ATP in our cell systems, but I'm going to focus today on ATP. So ATP is like money. In order for a human to operate on this planet, for me to sit here and talk to you this morning and to think and to wave my hand around, to go for a run, to whatever it is that we're doing, we have to spend molecular money. And ATP is the primary energy dollars that we expend to do these things. So the primary function of the glycolytic pathway under physiological conditions is to produce ATP, ending with the process in the mitochondria. And secondly, to fill our glycogen stores so that when incoming glucose is lower, the glycogen provides a way for us to get to more molecular energy. All right. And then as the glycogen is filled and the ATP levels rise, then glucose is funneled off into fat synthesis. So one of the connected pathways here, as glucose rises, right, as it's going up, the incoming glucose, as it's rising, glycogen gets filled, ATP levels come up to the standard that we need within the cell. Now glucose is funneled off towards fat production with the activation and production of the carbohydrate regulatory element binding protein. Yeah, I know. I just call it CREB. That's quite a mouthful. I'm not the guy responsible for naming it, but this is a transcription factor that activates de novo lipogenesis, the production of fat, and the production of fat via this pathway is centered on triglycerides. And why do we do that? Why do we have the de novo lipogenesis? Again, think glycogen, because evolutionarily, right, back when we were hunter-gatherers and whatnot, we need or must have pathways that allow us to store energy. And fat is a fat storage system. And in fact, it's what our adipose tissue really focuses on, right? The glucose that comes past the liver and arrives at the adipose tissue is going to be also converted into fat. Why? Because we, as humans, as we developed and came through evolution, we needed a way to store energy so that when we move from one food source to the next, and I'm going to talk about this more today, we had energy stores to rely on to do that, right? Glycogen was one of them, and fat storage is the other. And storing fat and glycogen, for that matter, is also advantageous because we store water with it, right? So that then when we're accessing these energy storages, we're not just getting calories out in order to do things, but we're also getting water as a benefit here too, molecular water coming back into our system. Now, you'll notice on the right side of my diagram here that in red, I have the fructose uric acid pathway. And we need to think about how the connection to this pathway works and at what point are we accessing it. So as the glucose, as we move in a meal to a point where we move to hyperglycemia, which is pretty typical in the standard American diet, where somebody is eating 5 or 6 meals a day and the level of incoming refined carbohydrates is high. So we have a hyperglycemic situation and there are added sugars, which brings in the fructose. At a point where we reach a hyperglycemic event arriving at the liver, now the fructose uric acid pathway is going to be activated, and it's going to be activated in 2 different ways, minimum. The first is going to be the added sugars that come in, which can come in through table sugar. If you're eating a processed foods, and I'm going to give you some examples today, have high fructose corn syrups in them, as an example, and high fructose corn syrup has got over 55, it can have over 55% fructose in it. Agave syrups are more like 90% or even greater in fructose. Again, the processed food is going to have added sugar in it, which is going to have a fructose load. And fructose itself, when it arrives at the liver, is going to be processed directly into this pathway. The pathway will be activated. And the hyperglycemia becomes important here because, again, when you think about glycolysis, this is a regulated pathway, again, whose function it is to produce ATP, not a deficit, and to fill glycogen stores and then to utilize incoming glucose at that point to generate triglycerides. So if we exceed the amount of glucose that's functional in that pathway, which we do in a hyperglycemic event, the cell has to figure out what it's going to do with that glucose. Because you have all this glucose coming in, it's being phosphorylated into glucose 6-phosphate, and it's sitting there, and it's starting to build up. And at a certain point, that the cell says, we can't do this. We have all this stuff coming in. We have to get rid of it. How does that happen? It activates the polyol pathway, whose first enzyme is called aldose reductase. And so up to 30% of that incoming glucose at this point in hyperglycemia is now going to be pushed off into endogenous fructose. So you have fructose coming in from 2 different places. You have what I call the exogenous load coming in, and then you also have the fructose that is being formed by the polyol pathway. And all of that fructose coming in, unlike glycolysis, is going to be processed in an unregulated fashion. So it is going to be converted to fructose 1-phosphate by an enzyme called fructokinase. And you're going to see decimation of the cellular ATP. This is distinct from how glycolysis works, right? Because now we're going to disrupt the amount of ATP that we have. We're going to take it way down. Simultaneously to that, we're going to have this elevated, significant rise in intracellular uric acid, which is going to drive systemic inflammation with the activation of certain inflammatory proteins like JNK1, IL-1 beta, and so on down the line, MAP kinases, this whole slew of inflammatory proteins. You're going to disrupt the nitric oxide signaling pathway, which has significant consequences downstream in terms of cardiovascular disease, notwithstanding the hyperinsulinemia, right? The high insulin that is happening in the background here because of the hyperglycemia, right? And we know that hyperinsulinemia downstream is having also an effect on the cardiovascular disease platform. And then there is the issue of insulin resistance that is happening here. The main thing is at the level of the mitochondria now, and this is the thing going back to the fat storage that's happening off of glycolysis, we have the activation of de novo lipogenesis, a slightly different flavor of it because the maximum or the main type of fats that are going to be produced here because of another transcription factor, I'm going to get into detail about that in a second, results in free fatty acids being produced, or fatty acids being produced right in the liver. And so the main effect on the mitochondria due to the effects that I'm talking about here will be that we shut down beta oxidation. So instead of fatty acids moving into the mitochondria where they can then be burnt, right? We're moving away from burning here to produce the ATP, right? So we're not burning anymore. We're not generating that ATP in the mitochondria. And now instead, the subunits, or these molecules that are normally produced in the mitochondria, are now going to be shuttled out into the cytoplasm of the liver cell, where they're going to be converted into fat. All right, now let's take a deeper look at this. All right, so step back and please don't be scared by this diagram. And I get that we have equations here, but you know what? We have to talk about mechanism, and I'm not one of these guys that's going to wave my hands around at this point and go, well, it all boils down to insulin resistance. Let's get underneath this and start asking questions about just what the hell is going on with the metabolism. So when we look, again, on the left side in white and light blue, we have glycolysis, which I've just gone through talking about. In the red, we essentially have the fructose uric acid pathway. And what I want to do now is just illustrate, since you have this diagram in your head from the last slide, right? Now I want you to utilize that simplistic view of this. So on the left, very quickly, with the turquoise arrow, you see the carbohydrate regulatory element binding protein there, CREB. And we already talked about how that is going to stimulate de novo lipogenesis. Now on the right, and because I think we need the weeds here in order to have a better understanding how the significant rise in uric acid is having this effect, and I provided now here in red all of these major effects. So the first thing I want to point out, if you look in the center of this diagram, is the uric acid that we have generated in the liver cell. And what it does is it causes the translocation of this enzyme complex called NADP oxidase into the mitochondria, where we're going to generate reactive oxygen species that have been shown to inhibit an enzyme called aconitase. Now, what's the effect of this? The effect is you're going to interrupt the Krebs cycle. And when you do that, citrate is going to begin to accumulate in the mitochondria where it will be shuttled out. And I'm showing the citrate there in bright yellow so you can see it, because when it comes out, it's going to be converted into fat. So when we have activated, we have this hyperglycemic event. We have glycolysis that's pushing glucose because it's overwhelmed into de novo lipogenesis from that point of view. And then we have the high uric acid over here on the right, which is also activating de novo lipogenesis from another point of view. We essentially are generating to a large degree, and I'm showing the yellow, the sterol regulating element binding protein 1C there in yellow. This is the transcription factor due to the fructose uric acid metabolism that's activating. Basically, it's pushing the gene expression of the key enzymes that are required for generating fat in the liver, along with the CREB that's over there on the left. So the point is, we have reprogrammed the liver with this metabolism to produce fat, and this is the origin of non-alcoholic fatty liver disease, because we have oil droplets that are being formed directly in the liver. We have triglycerides that are being packaged into VLDL and pushed out into the circulatory system. And this is why somebody who's eating a high sugar diet, when they go to the doctor, find that their triglycerides are so high. It's because they're favoring this metabolics. And remember, when the liver gets all full of fat like that, it cannot function correctly, right? And we start to see these abnormalities down the road when you consider that somebody's eating this way for decades. Now, I also show in this, in a simple way, how this metabolism is contributing to insulin resistance, because those inflammatory proteins I talked about, JUNK1, IL-1 beta, and NF-K beta, right? I'm sorry about the jargon. I'm not responsible for naming these things, but those proteins downstream, right, are going to influence the regulation of insulin's receptor in the liver in regard to how that receptor is interacting with the insulin. And it can have two effects here, which have not been answered in the science yet. One of them is a hyperinsulinemic or high insulin situation as the insulin passes, because of the lack of ability of the insulin now to interact with its receptor. And then the second thing is, this could influence, and this is yet a question that needs to be answered, how the insulin is being cleared by the liver. And I have yet to see in the science, right, in the papers that are published in this area, a definitive answer, if there is one, in what we're dealing with there. Are we downregulating insulin signaling within the liver, or in general, or have we effectively interrupted an insulin clearance issue with that? It doesn't matter though, because downstream, this is going to contribute to insulin resistance, which is the argument that we hear about the type 2 diabetes and all these other chronic diseases. All right, and I think let's move on now to the next slide. Again, if you have questions, you can put them in the chat. I promise I will address them at the end of the presentation. So if we now step away and we ask the question about the fructose uric acid metabolism, and remember, I'm arguing this in the context of the connection between fructose uric acid pathway and glycolysis, and in fact, other pathways, which I'm not even going to try to get into here. It would just literally be too much. And what we're talking about is the hyperactivation of these pathways, where we have a situation where somebody's eating the standard American diet, 5 or 6 meals a day, where we have incoming hyperglycemia, added sugars, and in the evening meal, most likely, if it's an adult, alcohol contributing to these conditions, because alcohol also activates the polyol pathway. So if you have hyperglycemia in a meal and you have alcohol present, then you hyperactivate the aldose reductase. This is the first enzyme in the polyol pathway, and you start pushing glucose in a hyper activated way into endogenous fructose, which then collapses into these drivers that I'm talking about here. And so we see, and there's a strong clinical data for this, is in particular out of Johnson's lab. Richard Johnson has published hundreds of papers in this area over decades of work. We have clinical as well as significant numbers of animal studies. Fructose uric acid metabolism is one of the core drivers. It's not the only thing that's going on, but it is one of the core drivers of the diseases that I've been talking about here, of which most of the time on these Friday mornings, I'm talking about gout. This is a significant driver of the gouty condition. It's a driver of sugar addiction, cardiovascular disease, Alzheimer's, because don't forget, and this is important to mention, we have fructose metabolism in the brain, adipose tissue, skeletal tissue, in the intestinal tissues, kidneys, liver, and also I believe in the chondrocyte, which is the central biological cell that we have in our joints that drive homeostasis, right? That drive what should be the normal conditions in the joint being disrupted by the fact that most likely I believe that there's fructose uric acid metabolism going on there. It's important to mention because I have let it slip out of my mouth a couple times, this issue of sugar addiction. We know that fructose, for example, is preferred by all of the mechanisms that involve putting food in our mouth and getting it the macronutrients to the liver. There's strong signaling between the taste buds. There's strong signaling with the brain via the liver, along with hormone release. And then we have the gut-brain axis, again, which has a preference for the sweetness of fructose. And then we have brain metabolism itself, which due to the fructose metabolism there, has been shown to produce a protein called delta phos-B, which has the effect of driving the addictive state. And where this comes from, that statement, where it comes from, is from the substance abuse people that have looked at the level of addiction directly and asked the question, what's driving it? And that research has led to phos-B, which recently in metabolism science has been shown to be activated both by sucrose and by fructose. So what are the drivers therefore, of the pathological activation of these pathways? So let's just quickly step back and I want to clarify an issue. So why does a human operate this way when we hyperactivate these pathways? Because when we were evolving and food sources were scarce, I mean, we've all heard the cliche feast or famine, right? And so humans were moving from one food source to the next. So we have evolved specialized systems so that when we're in the presence of a hypercaloric event that allows our body to very rapidly store those calories in such a way that we could then access them when we leave that situation, both in fat and in glycogen. Now, fast forward to where we are now in 2022, and people are eating the standard American diet, which is 5 or 6 meals a day, arguably hyperglycemic at every single meal. The level of processed food, the added sugars and those kinds of things, bringing the fructose in, and the alcohol in the evening meals combined with all three of those things, right? The hyperglycemia and the added fructose coming in. And you have a situation where those pathways are being hyperactivated chronically, day in and day out, month after month, year after year. And because of the inflammatory events that we talked about, the relationship with the insulin resistance and so on, eventually we end up with these chronic diseases that are consequences of eating this way. So what are the drivers? The added sugar, fructose and glucose, the hyperglycemia, alcohol, and then something I didn't really get into here, the umami, right? This is eating because umami is important because it also activates fructose uric acid metabolism. And this is where we have proteins that are high in glutamate along with other molecules that come in when we break down cellular tissue, protein, into compounds like inosine monophosphate and adenosine monophosphate. These are also activators of this pathway. And in the standard American meal, it's not uncommon to have all of these things together, especially if somebody's eating processed food, because processed food in general combines, right? This industry has learned how to combine all of these things. They understand that fructose can drive food addiction, and that umami can also contribute to overeating certain kinds of foods. So when you take these compounds and you put them all into a processed food, then you can drive overeating. And down the road, where does this lead? Keep in mind, where does this lead? To the consequences, right? Which are this whole range of chronic diseases. So I want to give a couple of examples. I want to roll through this because I get these questions all the time. Well, then what is the foods? What are the foods that we should be concerned about? So this is a slide that I've used off and on for the last few years. And this is an example where you got a guy, I'll use me. I can remember doing this. You go into a pizza joint, you sit down. In my case, I have a couple of beers, right? And what does the beer have in it? Well, it's got alcohol. Right, beer also has purines, which are going to contribute to opening the fructose uric acid pathway, and most beer is going to also have a very high carbohydrate load. And you're drinking this on an empty stomach while you're waiting for your food to arrive. Right, so what are you doing? Think about the liver. You have this hyperglycemic event coming in. You have the alcohol. Right, glycolysis is going to be overloaded relatively quickly, and glucose is going to start getting pushed off into endogenous fructose. That's what's going to happen. Then I've got my large pizza that shows up, and the crust is going to not only have glucose in it, it's going to have added sugar in it. So you're going to have fructose load there. And then you have whatever you put on the pizza, right? The sauce is definitely going to have sugar in it. If it's got sugar in it, it has glucose and fructose. And then there are the breadsticks, right? They come in a variety of different forms. A lot of people are going to order those with a sweet glaze on them, and salt at the same time. Does salt have an effect here? Absolutely. It is another factor that opens fructose uric acid pathway, in particular polyol. Salt activates the first enzyme in the polyol pathway, right? And you have all of that on these breadsticks usually. And then the stick itself, glucose, fructose, yeah, right? Then we have the loaded salad. And that's going to have a commercial dressing on it. Most likely, there's going to be high fructose corn syrup in there. You say, I don't know about that, Dr. Pete. Just wait. I have an example. All right. And this is one of my favorites because back when I was teaching full time, we had muffins showing up all the time. That and the bagels in the break rooms, right? This is a glucose fructose bomb that's now hitting usually an empty stomach somewhere around, say, 8 or 9 in the morning, or maybe even earlier, right? What are you going to do? Those pathways, people, are going to be hyperactivated, absolutely without question. And then over here on the left, I've seen this, right? I've had people ask me about the heart-healthy oat breakfasts and so on. I've seen this in my extended family. Wow, that's all I can say. Look at the fruit in there. The oats, and then if they've added brown sugar to this or honey, honey is another one, 55% fructose. That is this, eating that, you're looking at significantly hyperactivated glycolysis and the fructose uric acid pathway right away in the morning. Usually these guys are going to be super hungry about an hour later, and this is because of the disruption in terms of the hormones that control the appetite, leptin, ghrelin, and then don't forget what I've already outlined about the fructose, right? The increased the need to eat more, right? The compulsive behavior to keep moving the spoon into your mouth, right? If you set two people down at a table and you put a low sugar meal in front, like the ones I'm going to describe here in a minute, in front of one person, low carb, and you put one of these standard American meals in front of the other, and you say, just eat how much you want. You can go back for seconds all you want. The person eating the standard American material off of, or the food off of their plate, actually in processed food, we could call it material if you want. Those guys are going to eat more. They're going to input more calories because they are being driven to do that. So this is an example of a common salad dressing. I blocked out the manufacturer of this, and you can see if you look at the ingredient list in this, besides seed oils, that it contains high fructose corn syrup. And you might look at the nutrition facts and go, well, Dr. Pete, there's not that much in there. I mean, it's only 4 grams. But then, how many people literally only put a tablespoon of dressing on their salads? I know I don't, right? There's no way. I like to add a lot of dressing to my salad. Here's a popular fruit drink that's sold at a boutique chain all across the country. And juices are in particular really bad. And remember, going back to my explanation about all of this, think about what's going on at the liver. High amount of macronutrient coming in, short period of time. Juice will do that. So drinking this off the rack is just as bad essentially as having a soda. Here we have a common soda on the left, and you'll notice there's 40 grams of added sugar here. Now, these particular sodas, if you spend any time like I do thinking about you guys out there and how you reverse these chronic diseases, right? If you pull down different bottles of this, you will see that they use either table sugar in these things, or they're using high fructose corn syrup. Just remember, table sugar has 50% by mass fructose in it. So you're not getting off the hook with this. In a sense, essentially, remember what I said about the hyperglycemic effect happening at the liver. Large amount of glucose arriving in a short period of time, plus whether they use table sugar or whether they use high fructose corn syrup, when you drink something like this, you're going to have a high level of fructose arriving at the liver. All right. And then on the right, I'm providing an example of, this is marketed as a sports drink, right? The idea that you go out and you work hard doing something, and then you need to replace the glucose. Now, this talk today is not centered on the physiology of exercise, but what I'm just going to tell you is this is absolutely crazy. Look at the amount of sugar that is in this. So 62 grams, I think. Yeah, or 63. That's massive. And if you're doing this during exercise, you aren't just going to overload your liver and go essentially right into de novo lipogenesis, the storage of fat, but you also are going to really spike your insulin. And the idea that you're burning calories, it ends right there, because when insulin is really high and the liver is in the storage mode, all those calories, you're not burning those calories. You are storing those calories as fat and driving the disease is the point I'm trying to make. So what do we do about this? Well, regardless of what kind of diet, and when I say diet, I don't mean restricting calories. That's not what I'm talking about here. I'm talking about an eating lifestyle and what that's going to look like. And if you happen to be a vegetarian, I don't have a problem with that. But what are the things that have to change in our lifestyle, right? We need to stop the sugar. The alcohol has to be moderated because it is a powerful activator of fructose uric acid metabolism. And we need to stop with the hyperglycemia. Now, if you happen to be somebody and you think that you're metabolically healthy, what I'm going to next talk about, you may object to, and that's fine. Basically, you want to stop the deadly triad, or you want to modulate it way down. If you listen to Lustig and you listen to Johnson, they will tell you, don't be doing this every day, right? You cannot, you should, or I shouldn't say cannot, but you should not eat this way every single day. Because if you are, the likelihood you're going to be my age and be suffering from a chronic disease is actually quite high, right? The percentage is quite high. So the sugar, the alcohol, hyperglycemia need to be ramped way down. You need to be eating whole, real food. This is food that doesn't come out of a package or a box, right? You go and you buy fresh produce, you buy fresh meats, right? And there's nuances about that. I'm not going to get into it here, but basically you cut the food up and you cook it yourself, right? If you do this, you should be able to reverse these chronic diseases. Now, I said there are nuances because in some of these diseases like type 2 diabetes, if you're full-blown type 2 diabetes and you want to reverse that condition, then you are going to have to cut into the carbs. That's end of the story. I coach this stuff, and I'm just telling you now, I don't know any type 2 diabetics that I've coached over the last few years that were in the process of reversing their condition that did not cut into the carbs. And this goes for the vegetarians too, right? If you're in the vegetarian lifestyle and you want to reverse diabetes, one way or the other, you've got to bring the carbs down. That is something that I've seen over and over and over again. If you're suffering from sugar addiction, the other aspect of this is you will need to eliminate the trigger foods. And the trigger foods, when you think about the biochemistry that I've attempted to teach you this morning, are going to be things that have fructose in them, right? The hyperglycemia may be an issue. And then you have got the umami foods because they contribute to driving appetite as well, and the overconsumption of certain kinds of foods. So you have to evaluate this, right? Cut into the carbs potentially, depending on what your metabolic needs are, what reversal you're actually after. The monitoring of biomarkers is important. Weight is one of those, right? You can monitor weight, and you can do it in a way that doesn't involve a scale if a scale is an issue. Like whether or not you fit into a pair of pants that you haven't been able to wear for 20 years is a good way to know whether your weight is changing or not. And then there are the issues that I don't have time to get into in this presentation today that involve exercise. And exercise is super important because of the muscle tissue, right? Second to the liver, and perhaps to the adipose tissue, right? The liver and the adipose tissue are working in concert, but arguably the skeletal tissue is second to the liver, the most important tissue that's there. And for glucose disposal, right? Getting glucose out of the circulatory system and utilizing it in a healthy way, that we need to improve our musculature for sure. And then you have the issues of stress and sleep. This is just to show you some references. I'm not going to dwell on this. That my assertion that chronic diseases can be reversed by changing how we eat significantly is true. I advocate for the plate method. Remember, I want to eliminate in myself to reverse the prediabetes that I reversed 4 years ago. And to put my gout in remission, I focus on the plate method. Eliminate the deadly triad, the alcohol, the hyperglycemia, and the fructose. So here is a rendition of a simple plate of food. You can break it into 3 segments. In the top 2, I've got roasted Brussels sprouts, and over on the right, I've got broccoli. How you cook them, it is up to you, and the amount is essentially going to be the size of a fist, right? And then we have the protein, which for a particular individual, depending on what their activity level is, will vary in its size. Now, if you're cutting into the carbs, there will be naysayers out there that are going to go, well, the keto diet, Dr. Pete, is high protein. No, it's not. It's moderate in protein. And the amount of protein that we eat is dependent on your level of activity. And it's something that you have to play around with and ask the question. We're monitoring biomarkers. what's going on with my biomarkers, how do I feel, am I recovering from exercise? Those are the kinds of questions that one answers as they move into this lifestyle. Here are examples of the way that I eat, and you can see in every case, well, except for the one down on the left, and I'll explain that in a minute, exemplifies the plate method. So this lifestyle is fantastic. It tastes great. I mean, one of the learning curve issues surrounding it is you have to rethink what your plate is going to look like, because now there's not going to be a massive pile of potatoes or rice on it. Does that mean you're never going to eat that stuff ever again? Maybe not. Every person is an individual, and you will need to ask the question, how much of something can I eat before forcing this hyperglycemic event? Because we want glycolysis, right? Again, these pathways are working together, and we want glycolysis not to be overloaded, because it's when it gets overloaded that it's going to start pushing glucose off into these other pathways, fructose, uric acid being the one that we really don't want activated very often, right? And so when you scan this, you can see that the food actually is fantastic. It's really awesome. I have a breakfast down there on the right that has flank steak and eggs. The picture over on the left is ground chicken cheese casserole that not only makes a great dinner, but also it is utterly killer with eggs. The biomarkers that I think that I look at in myself, right? I'm, at an age of 60, when I was diagnosed with pre-diabetics, with pre-diabetes, what I did was I turned around and I said, all right, I want these biomarkers measured. And essentially, your doctor may argue against this. So truthfully, you may have to go out and contract the blood work yourself. And I look at insulin and my C-peptide, right? Because over time, I want to see my insulin come down to essentially a fasting level that is essentially low. And I've talked about in other presentations what those numbers should look like. I'm not going to do that here. C-peptide is important because it gives you a better handle on what your insulin expression actually looks like. Full lipid panel. And there are some arguments about what you ought to look at in here. And again, I would leave this for, I have other presentations where I've talked about this. The big thing is that when somebody has been eating the standard American diet for decades, usually they have, in a broad sense, they have a low HDL and they have high triglycerides. That's one of the things that you'll see when you eat a low carb lifestyle that will switch right away. Well, it's not right away, but after a few months, you'll see that relationship switch. The HDL will come up, triglycerides are going to go down. You want the metabolic panel because you want to look at your kidney function and also your liver function. A1C, right? This is one of the first things, the most rapid things that are going to change when you go to a whole food type of eating experience. You're going to see the A1C, it should come down. Fasting glucose should normalize. This happens very, very quickly. Like I went based on A1C and fasting glucose, I went from pre-diabetes to being normalized in 52 days in terms of A1C and fasting glucose. The lipid panel took longer. Fructosamine. The reason this is important is because if you've been eating a diet that's high in fructose, this is going to give you a better handle on what the level of the attachment of fructose to proteins, hemoglobin, and so on in your system that is independent of looking at the attachment of glucose to red blood cells, which is what basically the A1C is going to tell you about that. And then lastly, you need to know what your uric acid is, because a significant portion of people in the United States suffer from hyperuricemia. And this is a strong indicator of metabolic dysfunction. It's a quantity that needs to be measured. And with that, I'm going to close. I'd like to thank all of you for being here this morning. I really appreciate it. You can find your way to me at www.drpetent.com. In the show notes, we have a free support group, a Discord support group. That link is there, should be there, along with my email and my daughter's email. Thanks again for being with me this morning. I'm looking in the chat right now. I don't have any questions, so I think I'm going to go ahead and close out. You guys have a great weekend coming up, and I'll see you next Friday.